Good evening to you all. All right, so welcome back. We want to continue from where we left off last time, still on matrices, but today we'll be talking about linear transformation, which is matrix mapping and linear transformation. All right, so last time we got to matrix inverses. Let's talk about it. We'll still talk about this later on, where we'll be talking about determinants, properties of determinants, and how determinant is very, very important in linear algebra and machine learning. And many problems we have in machine learning involve solving systems of what? Linear equation, systems of linear equation, and they are often represented in this form, right? Where we have your A, X, and your B. Your A is your matrix. This is the unknown vector that you are going to look for, and B. And we said that what is actually happening here is we are doing a transformation. So we are transforming this unknown vector to this known vector, right? Now where A is the matrix, I've said it, and X is a vector of unknown, and B is a vector of target value or outcome. So we are transforming this to that. Now to solve this is simple. In normal linear algebra, algebraic expression, if I have an equation like this and I ask you to solve, you will tell me you will divide both sides by 5. But in actual sense, you are finding the inverse. So you have the inverse and you use to multiply both sides. And that is what has been done over here. So you find the inverse of this because the X is the unknown. Then 5, we can say is a scalar, which can also be a matrix. And this is the target. So what I can do is that if I can find the inverse of my scalar or my matrix, I'll be able to get the unknown. So what is my inverse? Is 1 over 5 or 5 raised to the power negative 1. I multiply both sides by my inverse, and the inverse will be able to cancel this. We say that it will go towards unity. It will become 1. Then here, I'll be able to find out my unknown. So my unknown now is 2. The same analogy or the same principle or concept is also applied in matrices. If we want to find the inverse of a matrix, we're saying that the matrix inverse, what it does is that it undoes the effects of a matrix. So when a matrix is transformation, it will take one vector to take a vector from one space to another. If you apply the inverse, it brings the vector back to its initial state. So if you have a vector A here and you move it to a new space, which is B, now this transformation is done using a matrix. So if you want to undo the effect, you have to apply what's an inverse of that matrix. So what the matrix does, or the inverse of the matrix does, that it undoes the effect of what? Of a matrix. And how do you represent the inverse? This is how it is done. The same principle that you saw in the algebraic expression, this is the same thing that we have over here, right? So when you multiply the matrix by its inverse, or the inverse by its matrix, you get what? A unit or an identity matrix, which is like 1 that we saw in what? Multiplication. All right. So this matrix inverse is defined only for square matrices. Okay, that means you are dealing with a matrix of the same size. That means if you are the number of rows should equal to what? The number of what? Of columns. However, not all square matrices have what? An inverse. Okay, so matrices that do have an inverse, we call them they are invertible, or they are what? Non-singular. Okay, we call them non-invertible or what? Non-singular. So when a matrix is having an inverse, we call it invertible or what? Non-singular. We see singular matrices or non-invertible matrices very soon. Now, matrices that do not have an inverse are called non-invertible or what? Singular. How will you know that this matrix will have an inverse or not? That is a question that you ask yourself, but we'll find out. Now we said the inverse of a matrix is able to undo or it undoes the effect of a matrix. So what are the properties? Now the inverse of A itself is still A. That means when you have an inverse and you find an inverse of it, is still A. And we saw this when we were doing transposition, when we were transposing a matrix or even a vector. We said that if you have a matrix A, you transpose it and you transpose it again, you are still back to the matrix, right? The same thing over here. You have an inverse, a matrix, and you find the inverse again, you still be back to the inverse, right? Then the inverse of a product. The inverse of a product of two invertible matrices is the product of their inverses. Now, this we also saw it in transposition, that if you have A transpose, then B transpose, if they are multiplying, yes, we said this is the same as when we invert it or we reverse it in this order, right? We are seeing the same thing also here for the inverse. Okay, we are seeing the same thing here also for the inverse. Now, when you have two matrices multiplying, we find it inverse. It is same as when we reverse it with their inverse individual inverse multiplying. Okay, so you see how one application leading to another, right? The inverse of the transpose of a matrix is the transpose of its inverse. So if you look at this, now here I'll find the transpose of the matrix and I'll find the inverse. The same as finding the inverse and finding the transpose. It's the same thing, nothing changes. Now these properties, we see it again. The next thing is matrix mapping and linear mapping. Now this is more, or is going to more of abstract. So please, if you don't get it, please draw my attention. I can go back to explain it once more for you to understand. Functions are the fundamental concept in mathematics. Okay, so when you have a function, for example, I can have a function, right, f of x. Then I will define what this function is supposed to do, which is what? 2x, right? Now we said this, the x over here, that is our domain or our object, and the value we'll get over here, okay, which is this whole thing. Some people will say it can be y, which is also what? Our codomain or our image, right? Now this is a rule that has to be obeyed in order for us to get the result that we are looking for. So if you have f of 1, you will tell me the answer is what? The answer is 2, because the rule says 2 divided by or the independent variable. So a function is a rule that assigned to every element of an initial set called the domain. Okay, the domain is the independent. These values, we can assign them ourselves. Then when you have assigned your domain, the function will generate another set called what? The codomain or the image. All right. So if a function with a domain u and a codomain v, then we can say that f is mapping u to v. So here, if we are dealing with matrices or even vectors, we write something like this. What we are saying is that we are mapping, which is from u to v, but f is the one doing the mapping. So the transformation from this vector space to this vector space, or from the u vector space to the v vector space. That is a transformation. So we are transforming from one vector space to another, and it's being done by this function. We'll find out that matrices are all transformation. Okay, matrices are all transformation. Now we saw this last week where we have matrix and a vector multiplication. Practical scenario is when I have this vector, when I have this matrix, forgive me, A, B, right? And here is C, D. And I ask you guys to multiply this by this vector x1, then x2. Last week we learned that when you have a matrix, it's just a column. So we can have my x1 multiplying what? The column is A, B. We learned this last week. Then plus my x2 multiplying my C, D. We learned this last time, right? Yes. This is matrix vector multiplication. Now, this behaves like a function. Why? Because if you look at what you're actually doing here, this is of dimension 2, right? Now, after the multiplication, what dimension are you going to have? You are still going to have what? Another dimension, or 2, because your answer will still be of 2 dimension. So what are we doing? We are moving or mapping this vector from this dimension or this space to a new space. We are mapping this vector from this dimension or this space to a new space. So for any m by n matrix A and a vector of any dimension, the product, which is AX, is a vector in a new dimension, which is this a new dimension is talking about, but it can be the same dimension. For example, here the dimension of the vector is 2. After the multiplication, we also get what? 2. Okay. So what we are doing here is the matrix here is the one doing the mapping, and matrices are known as transformation. So they will transform from one space to another. All right. So for any matrix which is of the size m by n, we define a function which from this dimension to this dimension. So what do we call it? We call it matrix mapping. We are mapping, so we are mapping from one dimension to another. We are mapping from one space to another. So here we are mapping. What are we using it to do the mapping? We are using the vector A. So the mapping is being, we are using the matrix, not a vector, please forgive me. We are using the matrix A. The matrix A is the one doing the mapping. The matrix A is the one doing the mapping. So it's mapping our vector here, okay, to this. So this is how the mapping will be done. So once we move from this, we'll get to a new dimension altogether. All right, so although a matrix mapping sends a vector to vector, okay, it is much more common to view functions as mapping point to point. Now, when I have a vector of this 1, 2, 3, you are going to tell me that this is indeed a vector. But if I draw a 3-dimension plane, you will tell me that this is a point. It's a point in 3 dimensions. So this, although we are mapping from vectors to vectors, but in actual sense, we are mapping from a point to point, because a vector is a point in that space. So if you are dealing with n, whatever dimension, if it is a 10-dimension or 5-dimension, in that space, that is a point. That is a point. So you are mapping one point to another, or from an old point to a new point. Okay, so what is linear transformation? In machine learning, our interest mainly lies in transforming the data. And this, we see it in our next module that we'll talk about, our next module that we'll organize, which is the calculus one, where we'll be dealing with neural networks. In this module, we're not going to talk about neural networks, just linear algebra. Now, when you truly understand linear transformation, neural network will be something very, very easy, because all the deep learning models, they are transforming data from one space to another. And this, the first time I saw this, I was surprised. When you have a straight line, or a number line, and I have some data here. So let's assume here is A, here too is A, here is B, then here too is A, and here is B, then here is what? B. Now, if you want me to segregate this data into A and B, it will be difficult for me to segregate this because this is one dimension. So for me to segregate this is going to be difficult because if you look at here's AA and look at it, how do you want me to draw this? You want me to draw the line, a straight line here, or I should draw a straight line here? Or I should draw a straight line here. You're not going to get a perfect line to what? To separate it. That is going to be difficult. How do you do that? What I can do is that I can move it from the 1D to 2D. And I don't have space to draw this. When you move it to 2D, you see that you will be able to separate, but it will not be all that okay. So one of the things that this algorithm uses, support vector machine and other algorithms, what they do is that anytime they want to separate or classify data points, they move it to a higher dimension. That means a higher dimension. When you move it to a higher dimension, we say that you've gone into a higher, there's a term they even use, forgotten the term, is it hyperspace? Yes, a term higher than the third dimension or tensors. Okay, so when it happens like that, it's very, very easy for you to be able to segregate this. Okay, and that is the same thing neural networks they do. Okay, that's the same thing they do. Okay, as I said last time, sometimes if you don't understand the math behind this, anytime you are doing some of these things, I mean, you yourself, your focus mostly is the coding. But when you understand, okay, so this is the math behind this, then you begin to appreciate it. Okay. Now, one of the key components of models in machine learning is linear transformation. As we said, we are transforming from one space to another. So linear transformation and linear mapping, I mean, the same thing. So here's somebody talking about linear mapping. I mean, the same thing or the same thing as linear transformation. Okay, right. So let's have two vectors, which I have a vector space U and a vector space V. Now, if I want to map from this vector space U to vector space V, I can have this. You remember we spoke about the linearity and the bilinearity when we're talking about vectors. Okay, so here, when you look at this, okay, when you look at what you have over here, it's like the function here is acting on the individual, right? It's acting on it. Now, what is happening here is, we'll talk about it, I mean, in the upcoming slides, but what is happening here is that we are still maintaining two things that we learned when we spoke about linear algebra, which is addition and scalar multiplication. If you look at it, addition and scalar multiplication is still being maintained, or that condition is still being kept. So if you look at it, the F is going to act on the first, and the A is still multiplying that function. That is the scalar multiplication. Then the second part, then we add it. So you see, our operations are being conserved. The addition and the scalar multiplication are still being conserved. So that shows you that it's a linear transformation we are doing, because we need to obey the axioms of our vector space. So a linear transformation is mapping between two vector spaces that preserve the algebraic structure, as I've explained, the addition and scalar multiplication. So these structures have to be preserved. When it happens like that, then that's why we call it a linear transformation. If these two structures are not preserved, that is not a linear transformation. So a translation is not a linear transformation. A translation, I believe you know what a translation is. Okay, so you have to, when you translate, okay, that is not a linear transformation, because you might not be able to pass through the origin, okay, and you'll be able to preserve our structure, the addition or the scalar multiplication. Okay, so let's look at this. Now, if I want to, I have a matrix over here, and I want to find a transformation, okay? If I want to find a transformation, I'm coming. Okay. Okay. All right. So I have a matrix. I want to find a transformation, right? So this vector is going to transform our objects or our domain over here to an image, right? So you tell me that it's going to be this, which is 2, 3, -1, 0, 4, 1. Then, which we have what? You have -1, you have what? 4. All right. So this, you are going to tell me we can pick the individual columns, right? Now here, what is the dimension? The dimension is 2, 2. So which is 2, -1, 0. That is the first one. Plus 4, which is 3 here. 4, then what? 1. If you multiply this, you are going to tell me that it is -2 here, right? Then 1 here, then here is 0, right? Then plus, what do we have? We have 12 here, right? We have 16 here, right? We have a 4 here. So if you sum the two, you end up getting uh, 10, right? 17, then what? 4. I believe I'm correct, right? So here, this matrix has transformed our vector toward a new image now. So I want you guys to take 3 minutes, okay, and complete the question number 2 for me. 3 minutes, I'm setting the timer. 3 minutes, complete the question number 2 for me right now. 3 minutes. 3 minutes. When you finish, you can type your answer in the chat. Okay, so uh, Joshua said it's 0, 0. Okay, who else? Okay, Daniel is saying it's 0. All right, guys. So sorry. My my data. So I think it's supposed to expire today. I didn't know. So 0. So that is okay. So all right. Okay. Now let's look at something over here. I believe you can hear me clearly. So we have this. Please take your pen and paper. We are going to work this thing along. So I have a vector over here. So we pick the vector, or we see the as formation, right? Is the one doing the. So we've got to transform. Sorry, we see a matrix. No, sorry, right? I see a vector. Sorry. So we see this matrix as the one doing what? The transformation. So it's going to act on these bases. Now I believe you know these bases, right? Okay, so you know these bases. So we did this, that was last week, yes, where we said when you have a vector and a matrix and you multiply a matrix by a base, you're able to get that column. So here, there are two columns here, which is the first column and the second column, right? So if I do the transformation using this, I'm able to get a first column. If I do the transformation using this, I'm able to get a second column. Now, this thing should tell you something, that with when you have any vector, we realized, or we saw that when you have any vector, so for example, a vector 3, 2 over here, right? This vector, we can construct this vector using the basis, right? So I'll have 3 here, then which is what? 1, 0. Then I also have what? 2 over here, which is also what? 0, 1. That means any vector at all in whatever space that you are dealing with, we can construct using, we are dealing with relation. If we can apply the transformation to the basis, it's the same thing like applying the transformation to the vector. Let me take it again. We said when you have a vector, because of linear combination, we can construct any vector using the individual basis. So I have a vector 3, 2 over here, and I can write it as a linear combination 3, then E1, which is the base, then 2, then what? E2, right? Now, what am I doing? This is a scalar. So this vector, I can construct it just multiplying the scalar by the individual basis. We have a major transformation to the vector because the vector can be written as a linear combination of the bases. So when we have this, then it's quite, by looking at, I have this vector, I'm doing this transformation on this vector. What did I do? Now you saw this, you saw that, right? This was the transformation we had when we applied to or the image, the image we had when we apply the vector, sorry, the matrix to this transformation, 0, 1, 0, no 0. When we apply to 1, 0, okay, then when we apply the same matrix to the base 0, 1, we had this. So what are we doing? It's the same linear combination that we are doing. So if I can apply So if you look at what we had over here, okay, if you look at what we had over here, which this is the base, we apply, we had this, we apply, we had this. If I have this vector, just simply transforming the individual bases, what I have to do is just pick that vector and put those values over there. That is what I'll get. It's simple, okay? Okay, so this can be written as this. So if you put it in a more generic way, applying the transformation to the basis, that means if you want to apply or you want to transform any vector, you just simply apply the transformation to the base and multiply it by the individual vector. So if I have a matrix, let's say 4, -1, 3, 2, and I want to use this matrix to transform this vector to -4, according to this, if this is in a vector space, which I can construct this 2, 1, 0, then -4, 0, 1. According to this transformation can be written as my 2 over here. Then I apply the transformation rather to the base, right? Which is 1, 0. Then plus, if you look at it, so here -4, so it's supposed to be -4 because that place is -4. So -4, right? Then I have my transformation 1, 3, 0. Then I'll have 0, 1. I guess something like this. Okay. So you see the importance of these bases. See the importance of these bases. So the result of this transformation, I just have to multiply by the vector and I'll be able to construct it. All right. So the images of the standard basis vectors are just a column of A. As you can see, we see that any vector, is of the dimension n. So the images, as you can see, so here to give of this, we're going to get this column. Oh, sorry, here is supposed to be 3, 2, not 0. I made a mistake. Should have corrected me. Here's 2 here. Your 2 is also 2. Oh, sorry. 2 here. Okay. Okay. So with the same linearity here, okay, from the explanation I've given, we can, okay, here is supposed to be plus, sorry. So we can apply it to that which you can see over here, what we are doing over here, okay. The same thing is the scalar, okay, structure being employed over here. So if you apply the transformation, we've seen all these things already. We said the scalar multiplication and addition what is conserved. All right. Now, when you take any transformation, the only transformation that goes to 0 is a 0 vector, the transformation what will go to 0, right? So when you have a vector like this, can also be put like this, and then can write 10 plus 0, which is correct over here. So that's the same thing that has been done over here. All right. Now the next thing is composition, how you try to have a composite of this transformation. Okay, a composite of this transformation. So we can have f of j, f of j, then we have our x. The same thing is what is being done here. So here, f of j, so that j will act on the individual components being done over here. Then the f will now act on the result. So when the j acts on it, the f will now act on the individual results. So here, addition and scalar multiplication is still being maintained. Okay, so if you look at this transformation, what are we doing over here? We are just scaling, okay, or we are stretching a vector. So how do you stretch a vector? We've seen this thing already by multiplying by what? By a scalar. Okay, so we have a vector at one point, we try to scale it or stretch it to a different point. That is linear transformation. Okay, so the same thing also is being done over here. So still the scalar multiplication and the addition condition is still being maintained. Okay. Now we saw this earlier on that when you have a vector, which you have a matrix, you want to map it from one space to another. So U is a vector space and it's having its individual basis, and also V2 is also a vector space, also having an individual basis. That means if you are mapping from U to V, okay, I can use the basis in U to be able to move it from U to V. And when I get to V, the result that I can also get in V, I can also present it in the basis in V. So a practical scenario is when we have a vector 3, 4 over here, okay, which you can express it as, you can express it as 3 here. Then I have 1, 0. Then I have what? 4. Then I have what? 0, 1, right? Now that is my U. These are the bases. Now if I should add this to another vector, which is -1, then let's say 2. If I add these two, you are going to tell me the answer is what? 2, 6, right? Now this answer that I've gotten, which is the image of this, I can also use a different base. Let's assume I want to use the same base. So I can also construct using a base which is 1, 0 here, then plus 6, then also what? 0, 1. I can do this. So that is what they are trying to say, that we mapping from U to V, we can use the individual basis to do the mapping. As you saw earlier on, that the mapping is actually done using the basis, because when you do the transformation on the basis, the same thing is like you multiplying the vector by the transformation on the base. So this is a practical scenario where here we have a vector x, and we can construct this vector s using individual base. So a vector s can be any vector at all, which is 2, 1. How do you construct it? Simply 2, then 1, 0, then here plus 1, then 0, 1. That is what is being done over here, right? Now I want to apply transformation to my vector, and we saw that instead of applying the transformation to the vector, let's apply the transformation to the basis instead. So instead of we applying the transformation to the vector 2, 1, why don't we apply the transformation to the basis first? So I can have f, which is 1, 0. Then I can also have another f, which is what? 0, 1. And that is what is being done over here. Now this is very, very important, because we will see that it is from this that we have what is known as vector matrix addition and also matrix multiplication. So when you apply the transformation to the base, we end up getting a matrix out. We end up getting a matrix out. Now, the results we are getting over here, as I did explain, is also a vector, which is V, but it's being multiplied by a scalar. And I did explain to you previously that when you add two vectors, you get a result. You can also have the results, you can also express the results in terms of basis multiplying by a scalar. So you applying the transformation to the base in the U space, we transforming from the U to the V is the same thing as we multiplying by a scalar. Okay. So now it's actually the matrix that is going to do the transformation, and that is what you can see over here. Okay, that is what you can see over here. So how do you get this? Let's find out how you get that. So when you have this, we apply the transformation. The transformation is being applied on the basis. Okay, so if you look at this is my vector, and look at the transformation being done over here. Okay, now when you look at this transformation that you are seeing over here, as you can see, this transformation that you are seeing over here, you guys will agree that this is like a matrix multiplying what? A vector. Because if you look at the dimension, this should agree to this. This should agree to this. So it's the same thing like the vector multiplying the matrix, or the matrix the vector, and through that we're able to get all images. Now, we'll have a practical example and be able to understand what is actually happening over there. So this is our matrix, this is our vector, and this is the result that we are getting. And that over here, okay, matrix is multiplying what? Our vector, and it's multiplying the vector, which if you pick the x1, okay, is going to multiply the column y. If you this is going to multiply that. If you pick that, is going to multiply that. Right. Now, how do you? We will see practical examples earlier. I mean, in the next slide, or the slide that will be coming. So we can add functions. We can also compose them. Now, this function we compose, add. If we look at this, let's pay attention to this. Okay, so here the F will add on this, the G also will add on this. This is what we are getting. Now, when we applied it previously, you end up getting our individual matrix. And if you look at it, this is like addition of what? Matrices. Because if you look at the dimension has to be, and also, yeah, the dimension has to be the same before we can add. So even when you compose the matrices that we use in transformation, it's also equivalent to what? You adding. For multiplication too, we can also have the same thing over here, where we want to multiply two matrices. Same things like we transforming one, then again we transform again. So we transform this with the gene, then we transform the. Now when you follow the previous calculation, you end up getting this, right? Which is that this is matrix multiplication that we are doing. By looking at it, you see that the inner dimensions are equal, k and k, so we can multiply. So you see that linear transformation, we can use it to add two vectors. We can also use it to multiply two vectors, right? Sorry, two matrices, not vectors, two matrices. All right. So what we want to talk about is inverting, linear transformation. That is finding inverses of matrices. This is a linear equation, and we can get our vector out. Then this is our targets, and this is the unknown. We have seen this thing already. So how do you do that? We have seen this already, that you form an equation like this, and with this equation that you form, you can find the inverse, use the inverse to multiply, so our unknown can be calculated as this. Now, the inverse matrix, it said it might not always exist, but when it does, it's extremely important for several reasons. We'll find out. The same thing can also be applied when we are transforming, which is linear transformation. So when you have a transformation of the same function, okay, you end up getting the individual bases. So if I want to transform on a base, then I find the inverse of that transformation is the same thing as the base, as you can see over here. Okay, so you have an inverse, a transformation, then you find the inverse of that transformation on that transformation again, you end up getting the individual bases. Okay, now we saw earlier on that not all linear transformation are invertible, because when we deal with the matrices, we saw that if so the inverse of a matrix, if the inverse exists, we say it is what, uh, non-singular, okay, or invertible. So you said not all linear transformation are invertible. That means when you get zero, it's not, it's not invertible. So if F maps all vectors to a zero vector, you can define the matrix. So if you remember what you did, the calculation, the exercise asks you guys to do, where we had the vector being what, zero, you had zero like this. Then you realize that that transformation is not invertible. That means uh, when you find the determinants, it will be zero, and we'll do that. Okay. All right. So change of basis. Now, this you've seen it over and over again, and we saw that in our first lecture. The base is like a perspective. Okay, the way you are looking at your grid, that's how the base is. So if you have your base, which is 1, 0, then 0, 1. This is your popular base that we've been using for the Cartesian coordinate. Okay. Now I can also change the base. I can also change the base. Now, when you are applying transformation, what is actually happening is what we are trying to, distort the grid. Is the grid that we are distorting. Okay, we are distorting the grid. So let's look at this. We have a transformation on a vector of 2 dimensions to another vector of 2 dimensions. So we have this, these are the bases, right? Now, when we apply the transformation to this is the result, or this is the image. When you apply the transformation, this is the image, right? So if you look at the previous slides, we saw that when you apply the transformation, you end up getting, let's go back, let me show you this so that it will make sense. So when you apply the transformation, this is what I'm talking about, okay? So you end up getting this, okay? So when you apply the transformation to the basis, okay, so when you apply the transformation to the basis, so when we apply F to 1, 0, right, we are getting 2, 1. Then we have this one to 0, 1. We are getting 1, 2, right? Okay. Now this will constitute a what transformation, where we can use it to build our matrix or the transformation. So here we have our 2, 1, then 1, 2. It is indeed true, because when you pick this, it's equivalent to this column. When you pick this, it's also equivalent to this column. Saw it previously. So by looking at the diagram, this is our basis. By we transforming it, look at where we are now. So look at this and look at that. Okay, so the transformation is done on this. The moment we can apply the transformation on the basis, we can get any vector at all. Now let's change the base. So we have a different base now, which these are 2 different bases. Now we have our transformation over here. So since you have our transformation, when we apply it, look at what we have to be able to know that you get -1. Now by getting this, what does it tell you? It tells you that when we have our matrix, which this matrix from our individual bases that we saw, now when we apply it to which is this and that, we end up getting 3, 3, right? We end up getting this. Okay. Then we also add that, we also end up getting this. So it's simply by looking at what we have is simply 3 of this. That means when I multiply 3 by my base, I'll be able to get that. Then if you look at the second one, it's just the same thing. It will not change. It's just the change. Okay, this. Oh. I want to hide. How can we hide this thing? So when you apply it, you realize that by looking at this, you just be multiplying this base by 3 and maintaining this same base. And if you look at that we are getting, matrix, why do I keep saying vector like that? The matrix we are getting for the transformation is this. So when we apply to the basis, look at the end result for the transformation. Okay, so it shows you that it's just we are multiplying out the first column by 3 and maintaining the second one. Right. Now, let's take our transformation to the Euclidean plane. And how is it done? Let's look at it. So when you have your plane, what is happening here is that you try to distort the grid. So we are the grid has been distorted, okay, by the basis. And we said, if this, you agree with me, maybe it will be the E1, then what? E2. But after transforming it, it might change. So we have different ways of this geometric mapping. You can stretch, you can do sharing, you can do rotation, you can reflect, you can also project. Now, all these things are very, very important in machine learning, also deep learning, also CV, computer vision. Okay. Sometimes when you are dealing with augmentation, if you're augmenting your data, okay, you just want to stretch, rotate, reflect. All these things are all what transformation that you are doing. So stretching, you've already seen stretching already. When you stretch, you take the vector from its position to a different, using the same line of the same line. So if I have a vector like this and I stretch it, I just extend it. You saw it previously. So this is the transformation. If I say transformation, I mean I'm talking about the matrix. So this is the matrix or the transformation for that. Okay. All right, so that is a practical scenario where we have our basis. So this is 1, 0. Then this is also 0, 1. Okay, and we have stretched it. So we stretch this to this place, also stretch this, but this one has been decreased, right? So that is stretching. Then we can also rotate. Okay, so rotation was also done using what? This transformation, okay, where the angles correspond. So 1, 0 correspond to this column, then the 0, 1 also correspond to this column. So this is so another form of what transformation that can be done. So we can transform where we pick the E1 all the way to this place, the E2 also all the way to this place. Then we can also do shearing, okay. Now this is needed a lot in those who are doing material engineering or material science. If you want to know the forces that are exerted on these subatomic molecules of any material, okay, when these forces are exerted or they exerted on these subatomic particles, what actually happens is that they also, change. So with that, you'll be able to study and know a lot about the individual forces that is, exerting on it. Okay. So this is the same thing that we can see over here. So we have this and it has been shared. Okay, it has been shared. So this was maintained, but this has been shared to this place. This is a transformation. Then also a reflection. Okay, so you want to reflect. Reflection is when you try to flip the axis. Okay, so you are flipping the axis. So here you can reflect in the x axis. You can also reflect in the y axis. I remember SHS, we did this rigid motion, rigid motion, rigid motion. They ask you to reflect it in the x axis, reflect it in the y axis. That was linear algebra we're doing, but at a lower level, we didn't understand. Okay. So we can also reflect in a higher dimension. So here we are doing a reflection in a 3 dimension, where here we have the E1, then here to the E2, then here to the E3. So here we are flipping the E3 to the opposite direction. Okay, we can also flip and rotate at the same time. Okay, so here we do flip, then we can also flip. So we are flipping and flipping again, flipping and flipping again. And as I said, these things are needed a lot in uh, augmentation. Okay, if you want to uh, change your data, especially when you're dealing with images. Okay, because if you have a picture of a cat and you turn the cat upside down, you turn it left to right, your model is supposed to be able to what? Tell you that there's a cat, whether you turn it left to right, you turn it upside down, a cat is a cat, right? So this transformation helps a lot for your model to be able to learn different orientation of your image, right? If you don't do that, your model will be static or yes, or rigid in only one way. So these rotations helps a lot. Right. The last one, then I think we are done, is determinants. Determinants. Now we saw the inverses. We saw that some of if the inverse exists, okay, we call it non-singular, but if it doesn't exist, okay, this one is singular. How do you know that whether your inverse will exist or not? And that one is determined by this guy, the determinant. The determinant also forms is having a geometric interpretation. Okay, things like volume, things like area, these are all determined by all your determinants. So we have a standard base, this and that, which I've drawn over here. Now, if I have a transformation and this is my transformation, I act it on this basis again, then I'll be able to have this. Okay, sorry, I wanted to show you, but let's go back. Now, this is my transformation. If I come back to my axis, that means I'm extending the E to this, the E1, which is the E2 here. Then also, now if you look at my area, the area has what? Has increased. Isn't it? So from this small thing, it has increased what to this. All right. So what is the determinant doing? Okay. Hello guys. Today, dear, please forgive us. Network is just worrying me. I'm not using my Wi-Fi. I'm using my phone network. Okay, so it's making the class some way. All right. So let's look at the transformation. All right. Now, if you look at transformation, you have a vector uh, 2, then also 2. Okay, drawn over here. Now, if I apply the transformation, you see that the new over here, what is actually happening? A lot is happening over here. This transformation has taken our vector to a new a new position now. If we can calculate the determinants, which we don't know how to do it now. I know some of you know how to do it, but we don't know how to do it now. As you are going to see that determinant 1 is a negative value. Okay, that is a negative value. So a negative value, what does a negative value of a determinant means? Okay, so the image on the previous slide represents the determinant with a negative value. So the negative indicates that the origin of the vector has, right? So if you look at our vector orientation, right? So if you look at it, you see that this is at a new position now. This one was here. Now look at this position now. Okay. So let's consider another one, which is matrix. Now, if you want to calculate the determinant, this is how the determinant is calculated, which we multiply the leading now, then we subtract it from the lagging one. So AD minus what? This is for a 2D matrix. What about a 3D matrix? How do you calculate it? So when you have a 3D matrix represents a volume. When the transformation takes, call it parallel pipette. Okay, parallel pipette. I don't know how it's pronounced, but I think it's correct. So I'll show you an example which you have your volume here, right? So when a transformation happens, you try to squish it. It's like a fat person sitting on a cube, okay, to try to slant it, okay. So that is the new transformation. This is actually done if you calculate that you actually know what is going to happen to your shape or your volume or your dimension. Right. So for this is how it is done. If you have your matrix, so if you have your matrix, the first one, which is this, then we pick this one, we multiply this, we subtract by that. That's what we have done over here. Then you pick this. The moment you pick that, you cross here, you cross here. So you pick this, so multiply this by this by this, subtract this by this. Then you pick the last one, cancel this. So we multiply this by this, then by that. So if you look at it, it's mating. So we start with subtraction, then addition, it goes. So if it is a higher dimension you are dealing with, you can continue by alternating this by going this, which is E, F, H, I, okay, S, B. If I should go on, then P, the minus on all the way. If you really want to go, you can go that way like that. This you can be able to reach determinants. All right, so let's talk about some properties of determinants. Determinants of the product of two matrices, just sort of finding the individual determinants and multiplying them. Then when we saw this already, the determinant of a inverse of a matrix is the same as the determinant of the matrix inverse. Then also the determinant of the matrix is the same as when you transpose it, the determinant of the transpose. Okay. Then if matrix which is of dimension that has two identical rows and columns. Now, if you have two identical rows and columns, then you agree with me that you have dependency. Okay, the vectors, one of the column depends on the other, or one of the rows depend on the other. And last time we saw dependency there, definitely the A or B was okay. So it will give you 0. Now columns are linearly independent. Okay, the columns are linearly dependent if and only if the determinant is equal to 0, and that is the explanation for here. Okay, you definitely have something like this: 1, 2, then give you, let's say, 2, let's right here, because this the second column expressed by multiplying the first column by 2. So here there's what? Dependency over here. Determinant. So this one, let's pick a square matrix, please. Sorry. So let me clean this. Let me clean this. All right. We find the here find 4 by 1. Okay. 4, then 2 by 2, which is still 4. We get what? 2. So immediately you see that if you tell it that, you give you 0. All right. And the last one, then we are done. So when you have a matrix of n by n, okay, in any of the, okay, the determinant will be 0. So what is saying that if here is 0, 0, then here is 1, 2, the determinant will be, all right. So so it can also be 1, then 0, 0. Okay, saying that determinant will be 0. Yes. Then the linear transform is invertible if the determinant is not equal to the determinant result, none of invertible. Okay, or that is what a singular matrix. And you don't want a singular matrix. Now, if you have a singular, something that we don't want, because you move from volume or area to a like it, you don't want. So you may have a matrix like this, sorry, a vector like this that is forming like this. If you find a transformation and we get a singular matrix, we'll move from this area to what? To a straight line, something that we don't want to happen. Okay. So I mean that is today's lecture. Forgive me, my network. I didn't know my bundle will finish, so that then I went off a little bit. Okay, but I will make it available on the, you know. If you have any question, let me. If you have any question, you can go on and ask.